All right, in this video, I'll talk about the definite integral, section 13.4, the algebraic approach, and the fundamental theorem of calculus. If something ever has a title like this, fundamental theorem of, it's important. All right, so this really matters. So the fundamental theorem of calculus, TFTOC. No, don't worry, I won't actually do that ever again. Let f be a continuous function defined on the interval from a to b, and if capital F is any antiderivative of little f and is defined from a to b, then we'll have the integral from a to b of f of x dx equals capital F of b minus capital F of a. Moreover, such an antiderivative is guaranteed to exist. All right, so hold up. What's this say? It says every continuous function has an antiderivative. You're guaranteed, if it's continuous, there's an antiderivative. And when we're given certain limits, these are called the limits of integration. When we're given certain limits, we don't even have a plus c anymore because we can find the exact values. So when we start with numbers here, our output will have numbers as well. Now, you'll get into other, that should be a number sign and not an asterisk. You might go into other calculus that's not oriented towards a business or a social sciences student, and you'll find that sometimes we can actually have expressions up here and not just numbers. But for now, we're just going to call them numbers, all right? Because we're first learning it. Okay, what does this mean? Okay, the integral from -2 to 1 of x minus 2 dx. Our first step, same as before. The antiderivative of x is x squared over 2 minus the antiderivative of 2 is 2x, right? What has derivative 2? 2x does. Now, we take that answer, and instead of adding plus c, we're going to actually find some real values. This little line means evaluate. So from -2 to 1, so we'll substitute 1 first. It's at the top. Always top minus bottom limit. Upper and lower, but fewer letters there. So I'll put 1 everywhere I see an x. I have 1 squared over 2 minus 2 times 1. Subtract, always subtract. So evaluate at the top number. Subtraction, evaluate at the bottom number. So I'll put -2 all squared. Notice the use of parentheses. Divided by 2 minus 2 times a -2. And then I'll simplify each one of these individually. This is 1/2 minus 2 minus sign. -2 squared, that's a -2 times -2, which is 4. 4 divided by 2 is 2. And -2 times -2 is a positive 4. So I'll have a 1/2 minus 2 minus 6. And that's a -8 plus a half. That's a -7.5. Like how I went from fractions to decimals are okay. Yeah. I'm just gonna stick by that. Sometimes it happens. All right. So the integral from 0 to 1 of this polynomial, 4x cubed minus 3x squared plus 4x minus 1 dx. Let's find the antiderivative. So we leave the 4. Antiderivative, we add 1. So x to the 3 plus 1 is 4. New exponent, new denominator. Minus 3. Antiderivative of x squared is x cubed over 3. Plus 4. The integral, right? Antiderivative and integral, same thing. Integral of x is x squared over 2. We add 1 to the exponent, divide by that new value. And then a minus 1 has antiderivative minus 1x. We'll evaluate this from 0 to 1. But here's something that's super cool. When you put 1 in, right, 1 to any power is just 1. So that's what we put in at the front. So we'll have 1 to the 4th minus 1 cubed plus 2 times 1 squared minus 1. And then subtract, because it's always top minus bottom. Subtract. When we put in 0, oh look, that's 0 to the 4th, 0 cubed, 0 squared, and 0. You get a whole bunch of zeros, and that's awesome. I forgot to mention here, because of these coefficients, they simplify really well. And if you noticed that as you were going here, hey, that's the derivative of x to the fourth, you could jump right to this step. If you don't recognize it, that's okay, because it'll turn up as long as you keep your coefficients and keep track of your details. And so as I put it 1 in, 1 minus 1 plus 2 minus 1, that's a positive 1 minus 0, so I get 1. Okay. The antiderivative, or integral, from 2 to 3 of x plus 1 over x. Now remember, we look at these individually. So the antiderivative of x is x squared over 2. Add 1 to the exponent, divide by that new number. The antiderivative of 1 over x, that's our special rule. That is absolutely important to use the absolute values. So the natural log of the absolute value of x. Evaluated from 2 to 3, so I'll put in 3. I'll have 3 squared over 2 plus the natural log of the absolute value of 3 minus, now I'll substitute 2 for x. I'll have 2 squared over 2 plus the natural log of 2. That looks like a bunch of 1s, but it's not. In absolute values. All right, so 3 squared over 2, that's 9 halves, plus natural log of 3. 2 squared is 4. 4 divided by 2 is 2, so I'll have a minus 2 and a minus natural log of 2. Distribute. 9 halves minus 2, this is 4.5. Minus 2 is 2.5. And don't forget your logarithmic properties. The natural log of 3 minus the natural log of 2 is the natural log of 3 divided by 2. And we'll keep the absolute values, although it's not necessary because 3 halves is already positive. Notice if we start with numbers here, we end with numbers here. Earlier, we were doing just general, no numbers here. We would have no numbers. We would have variables, a function that comes out. All right, but when we get specific, the definite integral, we definitely have a number that this is equal to. It's just finding an area. All right. So the integral from 0 to 1 of 8 parentheses negative x plus 1 to the 7th, that definitely looks like a substitution problem, so I'll let u be negative x plus 1. Du will equal negative 1 dx, and to get dx by itself, we'll multiply that negative 1 to the other side. Okay, so I can substitute, right? I have the integral 8. This is now u to the 7th. In place of dx, I have a negative 1 du. But you see, this x and dx, these are x values, an x value of 0, an x value of 1. But this integral doesn't have x values. It has u values. So we have to substitute twice. This time we'll just take care of it up front. So if x is 0 and u is negative x plus 1, then u is negative 0 plus 1, which is 1. If x equals 1, u is negative x plus 1, so that's negative 1 plus 1, which is 0. Notice how they're in different places. The x value of 0 had to become the u value of 1. It had to stay in the same location. So it looks like we just kind of switched the order of integration. All right, we didn't, all right, but that's what it looks like, so don't get confused on that. And the next one's a better example of that. So we have a negative 8 u to the 7th du. Let's take that negative 8 out in front. The integral from 1 to 0 of u to the 7th du, that will be, right, I have that negative 8 out in front. The integral of u to the 7th is u to the 8th over 8. And we're going to evaluate that from 1 to 0. The 8's cancel out. A little 8 cancellation here. So I'll have a negative u to the 8th evaluated top of 0, bottom of 1. So I'll put 0 in, and I get 0 out. Subtract what I get when I put 1 in for u. So minus 1 to the 8th. 1 to the 8th is 1. Minus a negative is addition. And so I'll get an answer of 1. I do not have to take it back to x. I've changed everything. So starting here and moving forward, it's like x never, it was never there, right? It was non-existent. Like this is just the integral that we had. Because everything is in terms of u, I never have to go back to the x. All right, that's what everybody wants to hear. I don't have to go back to the x. Okay. Yeah, lame jokes. It comes with territory. The integral from 0 to 1 of 5x e to the x squared plus 2 definitely seems like I'm going to use a substitution. So let's let u be that exponent, x squared plus 2. Derivative of u is 2x dx. And to get dx by itself, we'll have 1 over 2x du. So I have 5x e to the u, and then I replace dx with 1 over 2x du, and so my x's cancel, and I'll have 5 halves e to the u du. Now let's take a look at these limits. The 0 and the 1, they correspond to an x value. So if x is 0, my u value will be 0 plus 2, which is 2. When x is 1, my u value will be 1 squared plus 2, so that's 1 plus 2, which is 3. Upper limit of 3. Never have to go back to x because I've already substituted twice. All right, I've substituted twice. So we have the integral of 5 halves, the integral from 2 to 3 of e to the u du. It is its own antiderivative. That's why it's so cool. So we'll have 5 halves e to the 3 minus 5 halves e squared. And believe it or not, this is a great number. You don't have to go grabbing your calculator and find out what a decimal is. You don't always have to know exactly where it is. Sometimes just knowing what it is good enough. All right, last example. And this is a doozy. The integral from 1 to 2 of x times the quantity x minus 2 to the 1/3. All right. Obviously, it looks like there's some kind of distribution, but I can't because so we're going to let u be the inside. U is going to be x minus 1, and then du is just equal to dx. What does that get us? That gets us u to the 1/3, and it gets us du. But we didn't do anything with that x. That's easy to take care of. If we add 2 to both sides, u plus 2 equals x. And so I'll just, since there was no x here, substituting with my du dx, I can substitute x using my u. So that's u plus 2. The reason I do that is now I can distribute. But let's substitute our second time, right? This is considered the first time. It's a double substitution, but it's only once. Now I need to change my limits. When x equals 1, u is 1 minus 2, which is negative 1. Goes in the same location. When x is 2, so the upper limit, u is 2 minus 2, which is 0. So from negative 1 to 0, of u plus 2 times u to the 1/3. When we multiply u times u to the 1/3, that's u to the 1 plus 1/3. 1/3 plus 1, that's 1/3 plus 3/3, so that's 4/3. Same thing here, we'll have 2 times u to the 1/3 du. Antiderivatives or integrals will add 1 to the exponent, and that's our new denominator. Add 1 to the exponent, that's our new denominator, and we will evaluate from negative 1 to 0. Now, 4/3 plus 1, it's 4/3 plus 3/3, that's 7/3. Dividing by 7/3 is multiplying by 3/7. 1/3 plus 1 is 4/3. Dividing by 4/3 is the same as multiplying by 3/4. All right, still evaluating, still have work to do. So I'll have a 3/7 times 0 to the 7/3 plus 3 halves. This 2 cancels a bit with this 4 to give us a 2. 3 halves, 0 to 4/3, minus, always top, minus bottom. Now we substitute a negative 1 in here. Negative 1 to the 7/3, 3/7 times negative 1 to the 7/3 plus 3 halves, negative 1 to the 4/3. Negative 1's nice. See how this is all odd? Because we have odd powers here, this will stay negative. So we'll have a negative 3/7 inside these parentheses. That fourth power, that's going to be a fourth power of negative 1, and negative 1 multiplied by itself 4 times is positive. So it'll still be a 1. We only have to determine if it's positive or negative. So this is positive 1 after I do the 4/3 power times 3 halves. But this is 0 minus these, so that's a positive 3/7, a negative 3 halves. This is 6/14 minus 21/14, which is how I get the negative 15. I swear I know how to write a 4/14. All right. Definite integrals comes to us by the fundamental theorem of calculus. Now, both of these concepts, the U substitution and the definite integrals, will be helpful if you choose to do the extra credit for chapter 14. I'll have those videos posted soon.